The hand grenade. It is the quintessential battlefield tool, a compact device of pure, focused energy. For centuries, it has been an infantryman's final argument. But the simplicity of its function belies the immense industrial precision required for its creation. Welcome to the Wartech Forge. Today, we are going deep inside the factory that transforms raw metal into a fully operational battlefield detonator. Wide shot of the massive factory floor. Focus on the raw materials, steel coils or aluminum ingots. Our journey begins not in the armory, but on the factory floor, where massive engineering processes take over. Every grenade starts its life as raw. Specialized metal, often high-grade steel or aluminum alloy, selected for its strength and specific fragmentation properties. Show the metal strip being cut into discs, followed by the deep drawing press. The first step is forging the body. The classic pineapple shape, or the more modern, smooth body, requires immense hydraulic power. A disc is stamped from a metal strip and then subjected to a series of deep drawing operations. Imagine pushing metal through a progressively narrower mold until it forms a seamless cup. This process minimizes material waste and ensures wall uniformity, which is critical for safety and performance. For some designs, the body is formed from two hemispherical shells that are later precision welded together. This welding is a fusion process, often laser-guided, ensuring the body can withstand the enormous internal pressure of the explosion. The integrity of this shell is the foundation of the entire weapon. Close up on the interior knurling or the insertion of the internal wire steel matrix. A grenade's effectiveness is defined by its shrapnel, not just its blast. For fragmentation grenades, the shell must be engineered to break into specific, predictable pieces. This is achieved in one of two ways. Internal knurling, where a pattern is embossed onto the interior surface of the metal, or by inserting a preformed fragmentation matrix, a sleeve of spherical pellets or notched wire. This matrix ensures lethal fragmentation upon detonation, turning a simple explosion into a shower of high-speed projectiles. Shots of precision drilling and threading machines creating the neck and base holes. Once the main body is formed, it moves to the specialized machining centers. High-speed CNC machines drill and precisely thread the neck of the grenade. This threaded opening is where the delicate, yet crucial fuse assembly will be screwed in. Every thread must be flawless to ensure a tight, sealed closure. Shots of the body moving into a dedicated high-security area show controlled pouring, pressing of the explosive material. This is the point where the metal casing is finally transformed into a weapon. The grenade bodies are transferred to a secure, segregated section for the filler stage. The body is filled with the primary explosive charge, often composed of a material like TNT, trotyl, or high-density propellant grains. Visual showing the compound being tamped or cast under strict temperature control. The explosive charge must be uniformly dense. It may be poured as a molten compound that solidifies, or pressed under massive force to eliminate any air pockets. A consistent density is vital for ensuring a complete and symmetrical detonation, preventing any dud charges or irregular blasts. This process is monitored minute by specialized sensors, prioritizing safety and quality above all else. Transition to a different area showing small, intricate parts. Focus on the fuse components. While the body holds the blast, the fuse is the brain of the grenade, the sophisticated mechanism that controls the time of the explosion. The fuse is built from numerous, incredibly precise components. The striker, the firing pin, the primer, and the pyrotechnic delay element. Close up on the copper delay element, often called a delay train. The core component is the pyrotechnic delay, typically a chemical composition designed to burn for exactly 4 to 5 seconds. This delay must be manufactured and measured to microscopic tolerances, ensuring consistent timing regardless of humidity or temperature. A fraction of a second difference can mean the difference between life and death on the battlefield. Shots of the striker assembly being integrated into the fuse body, often using tiny automation machinery. The striker mechanism holds the firing pin under tension. When the safety lever is released, the striker is propelled by a spring, driving the firing pin into the primer, igniting the delay charge. The assembly of these components requires incredibly clean, automated environments to avoid contamination that could cause premature ignition. Show the complete fuse being screwed into the filled grenade body. The explosive filled body is now ready for its mind. The completed fuse assembly is carefully screwed into the threaded neck of the grenade body. This final mechanical connection is often sealed with a gasket or adhesive to ensure environmental protection, preventing moisture from reaching the sensitive explosive filler or the pyrotechnic delay. Focus on the final safety components being attached: the safety lever and the safety pin. Before a grenade leaves the factory, it must possess 2 layers of protection. The safety lever, the iconic spoon, holds the striker assembly in check. This lever is secured by the safety pin, the ultimate transport safety. This pin must be robust, enough to withstand rough handling, yet simple enough to be pulled quickly with a gloved hand. Shots of X-ray inspection, pressure testing, and random lot sampling. The final stage is the relentless pursuit of perfection. Every single grenade cannot be detonated, but every single one must be guaranteed to function. QC involves X-ray inspection to check the uniformity of the explosive filler, pressure testing the shell, and meticulous measurement of the delay element. Show a random sample being taken to the firing range or test bunker. Furthermore, sample lots are pulled and tested. These destructive tests confirm the integrity of the delay time and the efficacy of the fragmentation pattern under real-world conditions. Only when the data confirms flawless execution is the batch approved for final packaging. Shots of the grenades being placed in specialized crates with desiccants and labels. The finished grenades are packaged in airtight containers, often with specific climate control measures, to prevent stabilizer degradation and ensure a long, safe shelf life. They are labeled, documented, and given their unique identification codes. Wide shot of the vast factory complex, then a final slow-motion shot of a grenade being thrown. From a raw sheet of metal to a highly sophisticated battlefield detonator, the process is a marvel of industrial chemistry, precision engineering, and rigorous safety standards. This factory is a prime example of the power and complexity of the Global Machina